Welcome back everybody to Calculus 1. This is going to be a big video because at this point in the series we are finally going to talk about what's going to occupy us for the rest of the course, which is integration. And this is where things in calculus get very, very interesting if they weren't already. So I'm very excited to get into this. In order to get started, we have a very, very simple problem here. It says, imagine a car traveling at a constant rate of 20 miles per hour over the course of 3 hours. And we're asked to find how far the car travels over the course of the entire trip. You could probably figure this out. If the car is traveling at 20 miles per hour and it travels for 3 hours, it's 20 miles each hour, and that winds up being 60 miles. So the way that we're carrying this out is we're taking 20 miles per hour, multiplying by 3 hours. If you're a physicist, you'll notice all of these hours cancel, and you'll be left with 60 miles. Maybe you don't need to be a physicist to see that. Well, what I want to do is I want to think visually about what's going on here. And so I want to make a graph here. And on this graph, I want to plot the car's velocity as a function of time. And so on the x-axis here, I'm going to put time, and on the y-axis, I'm going to put velocity. And what would a graph of this car's velocity over the course of these 3 hours look like? Well, we know that the car's velocity is constant, and the graph of a constant is just going to be some horizontal line at 20 miles per hour. 20 miles per hour. And so if we were to plot that, we could just draw a straight horizontal line on the graph here. And what I want to notice is that this distance traveled here, right? We did 20 miles per hour times 3 hours. 3 hours is the length of this right here. And 20 miles per hour could be seen as the height right here. And so essentially, the distance traveled is the area under this velocity curve as a function of time. It is going to be this right here because we're taking this height and we're multiplying it by this base. It is essentially represented by this area here. And we're not going to dive fully into that yet. What we want to do is we want to see what happens when this velocity is not a constant value. It's something that changes. So with that in mind, I have this other example here. Now we're going to consider the case of a car whose velocity is given as a function of time. V of t is equal to 2t meters per second. And we're going to calculate how far this car has traveled after 3 hours. Now, at first, it might seem easy to do this, but this is kind of challenging. The velocity of this car is changing at every single instant along the course of this interval. And so, in order to calculate how far the car has traveled, we're going to have to approximate it at first. And the way I propose that we go about doing this is we take this time interval from 0 to 3 hours, and we break it up into even bits. And so let's say at first that we just want to break this up into 2 even bits. So I'll go here to 1.5, and I'll draw a separator here. And now I want to make the assumption, which is a wrong assumption, but I want to make the assumption that this car is traveling at a constant speed over these 2 intervals. And so let's just say that over the course of the first interval, the car travels at a constant speed of whatever the car is traveling at the end of this first interval after 1.5 hours. And let's make the assumption that at the end of the second interval, over the course of that whole second interval, the car is traveling at whatever speed it has at the end of that interval. And so if we were to make this assumption, it looks like we would say that the car is traveling at approximately a constant speed of 3 meters per second. And actually, we could just plug this value into the equation here. Our velocity at time is 1.5 hours would be equal to 3 meters per second. And here at the end of the interval, after 3 hours, the car would be traveling at a velocity of 6 meters per second. And so if we make this assumption, and we calculate how far the car is traveling now it's very easy. We know how to calculate these. We just did this in the first example. And so this is basically just 2 different problems similar to the one that we started with. We would take the area under these 2 rectangles, and we would add them together. And so that would look something like this. Something like this. And I'm not going to bother carrying out this calculation because what I want to point out is that this is obviously going to be wrong. We're making the assumption here that the car is traveling over the course of these constant intervals at whatever speed it was traveling at the end of those intervals, which is faster than however fast it was traveling over the course of the beginning of the intervals. You can see here, this is where the car was traveling. This is how fast the car was traveling at the end of the interval. But here in the middle, it's traveling at half that speed. And so assuming that it's traveling at a constant speed of whatever it had over the end of this interval is clearly going to result in a large overestimation. But what I want to point out here is that this idea is not useless because we could see what happens as we repeat this process for smaller and smaller time intervals. If here we break this up into just 2 different time intervals, and we take those areas, this is clearly going to be an overestimation. But it's not that big of a leap, for instance, to imagine breaking this up into 3 different intervals, and this would clearly give a better answer. It's still going to be an overestimation, but it's going to be less of an overestimation, because we're breaking this up into 3 even time intervals, and the room for change of the speed of the car over the course of those intervals is going to be less. Another way to say that would be, for example, the difference in how fast the car is traveling at the end of this interval and the beginning of it is going to be smaller than the differences to how far the car is traveling at the end of this interval and the beginning of it. And so clearly, if you break this up into more and more rectangles, it is going to result in less and less of an overestimation, and it will behave more and more like how the actual distance of the car will behave as you take the limit as this gets smaller and smaller. And so here you can see as this approaches 7 rectangles instead of 3 or 2, it would be once again a better approximation. But what we start to notice is that this begins to look more and more and more like the area under the curve, which we saw represented the distance under the constant velocity function. And so it's not that unreasonable to imagine that the area under this velocity over time curve represents the distance traveled. And since this is just a linear function which produces a line, a diagonal line here, and it forms a 90-degree angle here with the x-axis, this is just a triangle. And so if we want to calculate the area under this curve, we could do that very simply by just taking the area of this blue triangle here. And if we are correct in our assumption that this represents the distance traveled by the car, then we could have an exact answer in that manner. What's the height of this triangle? Well, it's just going to be this height right here, which is equal to 6 meters per second. And what's the base of this triangle? It's just this distance here, which is 3 hours. And if we want to calculate the area here, we would just have to do 3 hours times 6 meters per second divided by 2. This is just the formula for the area of a triangle. That would give the area under this curve, something like that, and this would be equal to 9, units of distance, because I used meters per second and hours, so this would just give 9 units of distance, but it would represent exactly how far the car traveled at the end of the interval, and this would no longer be an approximation. Now you're probably wondering why I even bothered with this whole mess about the rectangles. I did that for 2 reasons. Number one, in the first situation, when we're dealing with a constant velocity, we happen to notice that the distance traveled was equal to the area under the constant velocity curve. But it doesn't necessarily follow that that would be the same for these different situations where we have a velocity function that is variable with respect to time. It doesn't necessarily follow that that would be the case, and we have to demonstrate that. And the way that we demonstrate that is by showing that an approximation can be given by breaking this up into even time intervals and drawing these rectangles that correspond to the velocity that the car is traveling over the course at some point during those intervals, but the same point. And then breaking this up into smaller and smaller intervals will give a better and better approximation. And what we notice is that if we do that, as these get smaller and smaller, it does approximate the area under the curve. So we're right to assume that the area under this curve here does represent the distance traveled. The second reason that I did that is because that is going to be a useful tool for dealing with situations that are not this trivial. Here the area under this curve is just a triangle, and we know how to calculate the area of a triangle. Base times height divided by 2. Very simple. But now we're going to look at an example of a function where calculating the area under the curve is not so easy, and using this technique of specifically limiting the widths of these rectangles in order to, and then taking the sum of all those areas as we get more and more and more of those rectangles, is going to give us a very, very good, and indeed, as we take the limit, as the width of those rectangles approaches 0, it will give us a precise answer for the area under these curves where it's not so easy to work with them. So let's look at an example of that now. All right, so here's an example that's not as trivial as the last example. Here we're tasked with the goal of deriving a function capital F of x, which gives the area under the function f of t is equal to t squared over the interval from 0 to x. Now, I want to make sure that we fully understand this goal before proceeding, because it's a little bit complicated if we haven't seen anything like this before up until this point in calculus. So we're tasked to derive a function in terms of x, and the input of x here is going to give some interval under which we want to find the area of the function f of t is equal to t squared. So t is just some dummy variable here. This is a graph of the function f of t is equal to t squared. And what the function capital F of x will give is the area under the curve, under this curve, from 0 to x. So if x was here, for example, I'll do this in a different color. If this was our value of x, then our capital F of t function would give us the area, or our capital F of x function will give us this area here, the area under the curve f of t is equal to t squared from 0 to x. This is what our function is going to give us, and we're tasked to figure out what would this function be. And so let's see how we could start with this process. And so in order to do this, I'm going to consider some general x value here as an input into this function. And what we want to do is we want to find the area under this function, f of t is t squared, up until this point x on the x-axis, just as we previously highlighted. And the way I'm going to do this is I'm going to break this up into several different rectangles. And so I'll just draw some lines here. It doesn't really matter how many I do. But let's say that I draw this many lines or something, and then I'm going to start from the left side this time and draw rectangles that correspond with the heights at the beginning of the interval instead of the end. And this, of course, is going to result in an underestimation, but it will look something like this. Once again, I am a terrible artist, but it will look something like this. And this is going to give a decent approximation, it looks like, for the area under the curve. But the key thing to realize is if we take the limit of this as we make the width of these rectangles smaller and smaller and smaller, we will be able to find precisely what the area under this curve is. So just to be clear, we're talking about this area here. And let's see if we could think of a general way to calculate the area under these rectangles. Well, what I'm noticing here is if the rectangles are evenly spaced, meaning each one of them has the exact same width. This width is equal to this width, etc. The width that has to be is the length of the interval, which if this is ranging from 0 to x, is just going to be equal to x. So I'll write this here. The width of each rectangle, the width of each rectangle must be equal to the length of this entire interval divided by the number of rectangles. So let's say that n represents our number of rectangles. N is number of rectangles. And so the width of each rectangle must be equal to this. And if we can determine what the height of each rectangle is equal to, then we will be in business. We will have an equation that will give us the area of each one of those rectangles, and then all we have to do is sum up each of the areas. And so what's the height of each of these rectangles? Well, it appears to be the value f of whatever the beginning of these intervals is. And so what would that be equal to? Well, it's certainly easy to see that the height of the first rectangle would just be f of 0. And if we wanted to get the height of the second rectangle, we would have to move ourselves over one interval along the x-axis and evaluate the function at this point. And we know what the width of this interval is. It's just the same as the width of the rectangle, which is equal to this expression here. And so if we wanted to evaluate the function one more interval over from the origin, we would have to do f of 0 plus x over n. And that's just moving ourselves over one, and then this is just going to evaluate to f of x over n. Similarly, if we wanted to move over one more unit, we would have to add x over n again here, and we would get f of 2x over n. The next rectangle would be f of 3x over n, etc. One way of expressing this succinctly would be to say that the height of the, let's see here, I already used n as my number of rectangles variable, so I'll say the I plus 1th rectangle would be given by f of I times x over n. So if I want the height of the first rectangle here, I would have to plug in I is equal to 0, and that would give me f of 0. And that's exactly what we have. If I wanted the height of the second rectangle, I would have to plug in I is equal to 1 here to get 2, and if I plug that in, I would get f of x over n, which is exactly what we have here. So this is just a succinct way of writing this. The height of the I plus 1th rectangle is equal to f of I times x over n. And actually, we have done most of the work here now, and we can say that our capital F of x function, which is giving us the area under this curve after some interval x, is approximately equal to the sum of all of these little rectangles. So we'll start from I is equal to 0, and we'll go all the way up to the nth rectangle, and the height of each rectangle would be given by this expression here, f of I times x over n, where n is the number of rectangles, and then we would have to multiply by the width of each rectangle. And the width of each rectangle is just x over n. And so once again, this here, I'm actually going to color code this. This represents the height of each rectangle. So here, for example, on this last one, it would represent this. Right here, it would represent the height. And this right here represents the width of each rectangle. Each one of these little slices here is equal to x over n. And so when you multiply these two quantities together, what you're getting is the area of each one of these little rectangles here. And so if we take the sum of all of these from 0 all the way to the amount of rectangles that we have, what we're going to get is the total area of all of these different rectangles, and that's approximately equal to the function that we want, which gives us the area under this curve t squared over some interval from 0 to x. And if we want to make this function exact, all we have to do is take the limit as the width of these gets smaller and smaller and smaller, and as that happens, we're going to get more and more rectangles. And so a very succinct way of doing this would be to say that we're taking the limit as n approaches infinity of the sum from I is equal to 0 all the way to n of f of I times x over n times x over n. Here this is representing the width, and as you can see, if we take the limit as n approaches infinity, this is going to get smaller and smaller and smaller. Similarly, we are going to get an infinite amount of rectangles. And so this is no longer an approximation. This is actually equal to the area under the curve. And we could stop here, but I would argue that we could reduce this further and get into much, much easier terms. But technically, this is correct. This will give us a function that gives us the area under this curve over the interval from 0 to x here. And the key thing to realize here, if we want to simplify this further, is that this capital F of x function here is actually going to return the area under any function f from the interval from 0 to x. And that would we would just need to plug in different functions here. And so if we want to simplify this and make it more applicable to our situation here where we're trying to find the area under the function t squared, all we need to do is apply this function to this definition. And so if this is going to give us the area under the curve from 0 to x, all we need to do is plug in f of t is equal to t squared here and see what happens. And so in that case, we would get f of x is equal to the limit as n approaches infinity, the sum from I is equal to 0 to n, and f of ix over n here is just going to be this quantity squared. And so that's going to be x squared over n times I squared multiplied x squared over n squared times I squared multiplied by x over n. And we could pull these x over n's out of this sum because they're being multiplied over the entire sum. And so this is exactly the same thing as the limit as n approaches infinity of x cubed over n cubed, the sum from I is equal to 0 to n of I squared. And it might not seem like it at first, but we can actually reduce this even further. And the key is just dealing with this series here. And so let's take a break from this for now, and let's move down here. Let's take a break, draw a line, and we're just going to deal with this expression here, and we're going to see if we can find some alternative way of expressing this. And so if we move down a little bit, I'm going to rewrite that. We're dealing now with the sum from I is equal to 0 to n of I squared. And so what is this going to give us? This is going to give us 0 squared plus 1 squared plus 2 squared plus 3 squared, etc. 3 squared plus 4 squared, etc. And what does this actually translate to? Well, if we write out a couple different values of this, if this, for example, was a function of n, let's say f of n is equal to this, then what would f of 0 be? Well, if we plugged in 0 here, we would just get 0. And what would f of 1 be? Well, we would get 1. F of 2, we would have to add 2 squared here, and what we would get is 5. And if we continued in this fashion, we would see that f of 3, we would have to add 9 to the previous sum, and we would get 14. And then f of 4, we would have to add 16 to the previous sum, we would get 30. And this would imaginatively blow up pretty quickly, but here we would have to add 25 to the previous sum, and we would get 55. Once again, this is just the sum of the first 6 terms, the first one being 0, and so it would be the sum of these terms here, 1, 2, 3, 4, 5, 6. It would be the sum of all of those, etc. And what I'm noticing here is, if you look at this, there does not seem to be a pattern here. This function is not linear because the difference here is 1, the difference here is 4, the difference here is 9, the difference here is 16, not 20, and the difference here is 25. But what I'm noticing here is that this seems to be just the squares. And so there might be a pattern here, but if we look, we'll see 3, and then we'll see 5, and then we'll see 7, and then we'll see 9. And now it does seem to me that we have approached a constant relationship. And if this doesn't make sense, what this essentially represents right here is the first derivative. And what this represents is the second derivative. And what this represents is the third derivative. And so if you take the third derivative here, this is constant. This is not equal to the third derivative, but it's proportional. It represents the third derivative. And what we notice is if we take the third derivative, if we measure the rate of change of the rate of change of the rate of change, we're going to get a repeating constant value. And what function would have a third derivative that is constant? Well, I would argue x cubed. The first derivative of this is 3x squared. The second derivative is 6x, and the third derivative is 6, which is just some constant. And if we want to figure out what function would be given, we could derive in order to simplify the series, we might be able to assume now, or we've actually seen now, that it's going to be a cubic function. And so it's going to be some function that takes the form of this. It's going to be a x cubed plus b x squared plus c x plus d. And we can actually figure out what these coefficients are. And the way that we could go about that is by plugging in different values here. So we know that when we plug in the first 0 terms, basically where all of these x's is equal to 0, what we're going to get is d, right? Because all of these terms would then cancel and we'd be left with just d. And so when we plug in x is equal to 0, though, we're going to get 0. And so that's just going to tell us that d is equal to 0. Once again, just plugging in 0 for x's here, we'll be left with d. So if this was f of x, and we plugged in f of 0, we would get d. And here we're seeing that f of 0 is equal to d, and so d must be equal to 0. If we repeated this process and we took f of 1 here, that would be a plus b plus c, and we know that d is 0, so we can actually just drop that. We can drop that now. And so if we repeated this process for f of 1, we would see that this is going to be equal to 1. That's just this coming over here. If we repeated this process once again, we would get that 5 is equal to, and we would have to plug in 2 everywhere for an x here, so we get 8a plus, let's see here, we get 4b plus, we would get 2c. That's going to be equal to 5. And then for our next term in the series, we would have 14, and this is going to be equal to, we would have to plug in a 3 everywhere now, 27a plus 9b plus 3c. And now we actually have, with all of these, I can just replace f of 1 here with the 1 and move it away from this side. We have a system of 3 different equations, and we could solve this in order to get these coefficients, and we could determine a function which will simplify this series greatly. And so if you wanted to go about solving for these coefficients algebraically, it's not that difficult. You could solve for this equation in terms of a, for example. This would be 1 minus b minus c, and then you would have to plug this into both of these equations to get a system in terms of 2 equations. So you'd have 2 equations with 2 different variables, and then you'd have to solve one of those 2 equations for one of the variables that was left. In this case, it would be b, and then you would plug that into the other equation to solve for c, and then after all of those steps, you would be able to solve for all 3 of those coefficients, a, b, and c. It's not that difficult, but it takes a while, and I elected just to use a matrix in order to solve this. And so with the matrix, I just plugged in the coefficients here. I got 1, 1, 1, and 1. That's this first equation here. And then I did 8, 4, 2, and 5 for the second line here. And then the third line here would be 27, 9, 3, and 14. And then I took I solved this matrix for the coefficients. I got that the first coefficient a would be equal to 1/3, the second coefficient b would be equal to 1/2, and the third would be equal to 1/6. And so a here would be equal to 1/3, b 1/2, and c 1/6. And so once again, you could just do this algebraically. I just used the matrix. It's a lot faster. And so our f of x here ultimately would simplify to 1/3 x cubed plus 1/2 b squared, or sorry, 1/2 x squared, 1/2 x squared plus 1/6 x. And you could algebraically reduce this. You could factor out an x, and then you could play around with what was left, and you could get the typical formula for a sum of the first n squares. You could do that. However, what we're interested in here is the limit of this expression, the limit of f of x as x tends towards infinity. And what's going to happen here is that this x squared term and this x term are going to become negligible to the x cubed term as this expression approaches infinity. And so really all of these are just going to drop off, because the difference between a very, very large number cubed and a very, very large number squared, that same number, it's going to become negligible as that number tends towards infinity. And so the limit of this function is going to approach this behavior of just 1/3 x cubed as x tends toward infinity. And so we can actually use this and plug it into our equation above instead of this series here. And if we plug that in, we have a sum going from 0 to n, and so we have to do this in terms of n. And what we would get is, actually let me clean this up really quick. And so what's going to happen is we take the limit as n approaches infinity of this expression, now that I have some room, is that we're going to get x cubed over n cubed multiplied by this series, as you take the limit as n approaches infinity, is going to approach the behavior of 1/3 n cubed. And so when you multiply these together, these n cubes are going to be canceled, and magically we no longer have any n's in our terms. We're just left with, or any n's in our equation, we're just left with 1/3 x cubed. And so this is a function, f of x, which gives us the area under the curve x squared, x units away from the origin. And so we have successfully completed our mission. So for example, the area under the function f of t is equal to t squared on the interval from 0 to 4, for example. Well, that would just be 1/3 4 cubed. 4 cubed would be 4 times 4 times 4, which is 64, and so the area would be equal to 64 thirds. And that is exactly correct. That's exactly the area under that x squared function. Now, if that felt overwhelming, don't worry. This is just the first part in a series on integration, and we have tools in calculus that make this process so much easier. And so the point of this video was to show where these ideas come from. We started with a very, very, very simple example of a car traveling at a constant velocity, trying to discover how far it had traveled over some interval. And then we took that and we changed it to where the velocity of the car was changing, and we tried to figure out how far this car had traveled over the course of that interval. What we found out is that the distance that the car had traveled was the area under the velocity as a function of time curve. And so if you took the area under the curve of the car's velocity, you actually discovered the distance that it traveled. And this introduced us to the concept of why we might want to solve areas under different curves. And then we started exploring a situation where we have a curve where the area under the curve was much more difficult to calculate. It wasn't a simple triangle. We introduced this method of Riemann Sums, wherein we break up the area under the curve into several different rectangles, and we found a formula that gives us the approximate area under the curve, breaking that area up into n different rectangles, and adding up the area of each one of those rectangles. And we also found a precise definition for the area under the curve, taking the limit as the number of rectangles we use to approximate the area approaches infinity. We then use this definition in order to solve for a function that gives us the area under the function x squared in terms of just x, and we were actually able to completely solve that equation, getting rid of the rectangle terms in their entirety, and we were just left with 1/3 x cubed. In the next couple of videos, we're going to deal with situations where we're taking segments of areas, not just from 0 to x, for example, but, for example, taking the segment of the area under the curve from the point here to the point here, just as an example. If we wanted to solve for this area, that would be much easier. And we're also going to look at using calculus in order to simplify this process immensely. And what will we be left with is a method in order to find the areas under these curves that is just as fast as you could differentiate, for example. I hope that was illuminating. I hope it was interesting, and I'll see you guys in the next video.